This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace. Welcome everybody to section 4.7, day 2, theorems about zeros and polynomial functions. These are all going to be theorems that apply the skill of synthetic division or polynomial division. So here's one particular theorem. Let's say you have this giant, massive polynomial right here, and all the coefficients are integers, like these integers right here. Anyway, basically what you're saying is, what this theorem is saying is that the zeros aren't, if you have to guess what the zeros are, there aren't an infinite number of guesses to make. You can restrict the number of guesses you need down to some sort of fraction. So you take the possibilities for p, which are all the factors of 4. So 4 can be divided up, all the factors of 4 are 4 and 1 and 2, and then you make them positive or negative. Those are all the possibilities for the top of the numerator of this fraction. And then you take all the possibilities for q, which would be all of the factors of 3. So that's just 3 and 1 because it's prime. Anyway, the possibilities for p divided by q, the 0 of the function, would be every single possible fraction you could make from all the factors of this number and all the factors of this number. So all the different fractions you could possibly make look like this. These are all the possible zeros of the function. And that might seem like a lot, like plus or minus 1, 2, 4, 1/3, 2/3, 4/3. We're talking about 1, 2, 3, 4, 5, 6, 12 different possible numbers, 12 different zeros. But in the grand scheme of things, that's not too many. Like, that's, at least it's not infinite. You've only got to make at most 12 guesses before you find something. And so here's what you can see. I'm going to take as my guess 1. 1 is always a possibility because 1 divided by 1 is 1, so that's one of my guesses. And one thing I want to notice about this function is that it's missing a quadratic term. So the coefficients are 3, negative 11. You have to insert a 0 because there's no x squared term. And then 10 and negative 4. So here it is. I'm going to guess 1, and then I'm going to do my polynomial division. Bring down 3, multiplied by the 0, which is 1, add. Multiply by the 0, add. Multiply by the 0, add. Multiply by the 0, add. You get negative 2. Well, since it's not 0, since you get a remainder, then I guess number 1 is the value of 1 is not a 0. So we've got to try again. Let's guess something else. So let's guess negative 1. All right, bring down the 3, multiply by the 0, add. 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 Woohoo! We get a remainder of 0. That means negative 1 is a 0 of the function. Notice how when we write it like this, we can just draw another line right underneath it to make our next guess. I'm going to guess, you might have to guess more than this, but I know what the answer is, and I know that 2/3 is going to work, so we'll pretend to guess that next, just so that the video isn't too long. So then bring down the 3, multiply by 2/3, the 0, add. Multiply by 2/3, the 0, add. Multiply by 2/3, the 0, and we get 0. So 2/3 and negative 1 are both zeros, and the remaining numbers represent the quadratic expression. So it's x minus negative 1, which is x plus 1, and x minus 2/3. Funny, you can actually factor out a 3 from all these terms. 3, negative 12, and 6. They're all factors of 3. Multiples of 3, so you can factor out the 3 here. And you get x squared minus 4x plus 2. And that 3 can actually be distributed here just so that we don't have to deal with fractions. Like, distribute here, you get 3x and 2. Then, here, we're taking x squared minus 4x plus 2, and we can plug that into the quadratic formula, where the a value is 1, the b value is negative 4, and the c value is 2. I'm not showing the work here, but when you do that, you get this. You get 2 plus or minus the square root of 2. And so both of those answers become zeros of the function. So we've got 1, 2, 3, 4 different zeros. There it is. F of x is factored. And so that's what the instructions are. You've got to factor. All right, here's another one. Wow, look at this massive, massive polynomial to the 5th power. How in the world are we ever going to handle that? Well, if you look at the instructions, if you actually look back through and read the textbook at this point when they give this example, they say, rather than guess, because there's so many different possibilities, you could have 15 over 2, or 15 over 1, or 5 over 1, or 5 over 2, or or negative 5 over 2, or negative 5 over 1, which is negative 5, or 3 over 2, or negative 3 over 2. There's so many of those possibilities. They say at this point, rather than start making guesses and seeing if you're right, you should just graph it. And so, although it's to the 5th power, we see that there are 3 zeros right here. 1, 2, 3. That probably means that 2 of them are going to be imaginary or complex zeros. But I don't know what 2.236 is. Like, that's probably some sort of rounded square root. But I do know that we've got 0.5 as one of the zeros. So we'll start there. And so we get our first 0 from the graph. Rather than guess, they say graph. So we'll graph. Anyway, these are all of the coefficients. 1, 2, 3, 4, 5, 6 of them. And so we bring down the 2, multiply by the 0, add, 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 and there it is. 0 is the remainder. That means that we factored it correctly. And so what that looks like, because there's so many zeros here, what I'm going to do next is just write it out as the function. Because we guessed 1/2, then x minus 1/2 is one of the factors. 2, 4, and 30 are all even, so we can factor out a 2. And that 2 multiplies and distributes to get 2x minus 1 here. And so we're left with x squared minus 5 and x squared plus 3. Oh, how did I get that? I factored this doing basically a u substitution where u is equal to x squared. So my factor x would ask, what 2 numbers add up to -2 and multiply up to -15? Well, that's 3 and -5. So I get -5 here and 3 there. Continuing to factor, this is the difference of squares. So it would be x plus square root of 5 and x minus the square root of 5. And then here, we'd get the same thing. X plus the square root of 3i, x minus the square root of 3i. And those are our factors. This polynomial, this has now 1, 2, 3, 4, 5 factors, as expected, because it has a degree of 5. I went through that really fast, so if you have any questions on how I went from step to step, then I'd be happy to hear about them in class. Next example. Let's do this again. So we've got to the 3rd power. Let's pretend we can't use a graph to guess. We're in a testing or quizzing situation where we're not allowed to use a calculator. So we guess 1, and we do the synthetic polynomial division. And we see, bring down the 1, multiply by the 0, add, multiply by the 0, add, multiply by the 0, add. We eventually get -4, and that means that the remainder is -4, and so therefore 1 is not one of the zeros. So let's start again. Let's guess -3. I guessed -3 because it's one of the possibilities. Looking here, all the possibilities could be simplified versions of the fraction 6 over 1, or 3 over 1, or 2 over 1, or 1 over 1, plus or minus any of those. So one of the guesses you can make is -3, and when you do that, you get, you bring down the 1, multiply by the 0, which is -3. You get that, add, multiply by the 0, add, multiply by the 0, add. Great, we get a remainder of 0. That means that minus 3 has got to be one of the zeros. So x minus negative 3 is just the same thing as x plus 3. Then we have the x squared term. There's no linear term here, but the constant is negative 2, so that's x squared minus 2. I want you right now to tell me what this would be. When you factor it, you'll get 3 different factors. You get x plus 3, x plus something, and then x minus square root of 2. Can you figure out what that is? I think you can. Okay, so here, this polynomial function has a degree of 4. Let's pretend you're allowed to use the graph. So here, allowed to use Desmos or a graphing calculator. So we graph it, and we see immediately that there are 2 x-intercepts. That probably only means that 2 of them are real, and then 2 of them are going to be imaginary or complex. So I can see immediately that we've got 1/3 that's here, and then negative 1 that's there. Great. So what we can do is we take negative 1, which is the x-intercept, and we consider that to be one of the zeros. We line up all the coefficients, bring down the 3, multiply by the 0, add, multiply by the 0, add, multiply by the 0, add, multiply by the 0, and we get 0, which is great. That's a remainder. And then the other 0 that we got was 1/3, and so we can divide it all by 1/3. So bring down the 3, multiply by 1/3, add, multiply by the 0, add, multiply by the 0, add. Great, so we get 3, negative 6, 6. That translates to 3x squared minus 6x plus 6. And then I've got the other 2 zeros right here. Well, it looks like we've got 3, negative 6, 6. Those are all factors, multiples of 3, so we can factor out of 3. And then we get this right here. 3 times x squared is 3x squared. 3 times minus 2x is minus 6x. 3 times 2 is 6. So there it is. We can take the 3 and distribute it to here so that there's no fractions. Just it looks nicer. That's not really a required step, but you can do it. And then we get 3x minus 1 here. Taking the values of a, b, and c, 1, negative 2, and 2, into the quadratic formula, we see that we get as answers 1 plus or minus I. So that's what I have here. X minus 1 plus I, and then x minus 1 minus I. And it's all completely factored. We've got 4 different factors, and that's to be expected because the degree was 4. I'd like you to start on assignment 4G2, just like William H. Harrison would have when he was president and he did math. Actually, he was quite a mathematical president. Start assignment 4G2, copy the problem list, do the first problem, and I'll see you in class.